In this, and the next few videos, we'll explore heteroskedasticity, how to detect it, and how to correct it. In today's video, we'll begin with the graphical detection of heteroskedasticity and homoskedasticity. We'll study the data generating process, often called DGP. Here, we'll create both the independent and dependent variables, step by step. Next, we'll visualize the generated data using graphs, and then run ordinary least squares, OLS regressions, on both homoskedastic and heteroskedastic data sets. Finally, we'll compare the results to see how heteroskedasticity affects estimation accuracy. Have a careful look at this graph as we discuss a few examples of economic variables that may fit into this kind of relationship. Assume household income is measured along the horizontal axis and household expenditure is measured along the vertical axis. If we plot data for low-income families, the graph will look like the blue points, because their spending is limited and the variation is small, almost constant. Now, if we plot data for high-income families, the graph will resemble the red points, since their spending varies widely, showing a large and increasing variance. Similarly, when we measure firm size on the horizontal axis, say, by sales or assets, and plot their profits or profit margins on the vertical axis, small firms will form a pattern like the blue dots, while large firms will form a pattern like the red points. The same reasoning applies to education and wages. Individuals with low education levels have small, similar wages, while those with higher education levels show a much wider spread of income outcomes. So, the data represented by the red points exhibits heteroskedasticity, while the blue points represent homoskedastic data.
Now let's generate similar data using what is often called the data generating process, DGP. For our independent variable, x, we'll draw 200 random real numbers, uniformly distributed from 1 to 10. Algebraically, we write, x is uniformly distributed from 1 to 10. Think of x as an input, years of education, an income bracket, or firm sales. In Mathematica we use the functions random variate and uniform distribution to do this. Here are the first 10 observations out of the 200 values of x. To generate the dependent variable y, we use a simple regression model. Beta 0 and beta 1 are the intercept and slope coefficients, and u is the error term. We'll create two versions of the error term, one homoskedastic, with constant variance, and one heteroskedastic, where variance depends on x. Comparing the two will let us see how heteroskedasticity affects our regression estimates and their standard errors. Heteroskedastic error, or epsilon hetero, depends on x, the independent variable, and random noise drawn from a normal distribution. Homoskedastic error, or epsilon homo, depends only on random noise, not on x. By setting the intercept, beta 0, to 2, and the slope, beta 1, to 1.5, we generate two dependent variables, y hetero and y homo.
This is the scatter graph of y hetero versus x. As the error variance increases with higher values of x, the outcomes become more spread out. As we move away from the origin toward the right, the observations appear wider and wider. This is the scatter graph of y homo versus x. Here, the error variance remains constant as x increases. So, the spread of observations stays roughly the same throughout. As we move away from the origin toward the right, the width of the data points remains constant. This is the overlay graph of both scatter plots. Here, we can compare the heteroskedasticity of the red points with the homoskedasticity of the blue points. Have a look at the regression model in its general form with beta coefficients, and then in its specific form, where the coefficients are 2 and 1.5. In real life, these specific population coefficients are not known. From the collected data, we usually estimate them using the classical method known as ordinary least squares, OLS. These formulas for the coefficients can be derived using calculus, both in matrix form and in non-matrix form. Thus, using the data on the dependent and independent variables, we estimate the regression coefficients. Now, here is a table showing two sets of OLS results. One based on heteroskedastic data, and the other on homoskedastic data. The important point to note is that OLS becomes inefficient under heteroskedasticity. Although the estimated regression coefficients are roughly the same. The standard errors, and therefore the t-statistics, are quite different. 0.09 versus 0.02. And 14 versus 97. That is, heteroskedastic errors inflate the standard errors and reduce the t-statistics, making inference less precise. We can obtain efficient estimates with correct standard errors by using the estimation method known as weighted least squares, or WLS. Alternatively, we can use what are called robust standard errors. We'll study both of these methods in a separate video.